Welcome, students, to one of the most energetic and transformative chapters in our science curriculum. Since the dawn of civilization, the discovery of fire has been a turning point for humanity, allowing us to cook food, ward off predators, and eventually power the massive industries that built our modern world. But have you ever stopped to ask, what exactly is fire? It is not just a physical event. It is a profound chemical performance. In this chapter, we are going to look beyond the light and heat to understand the precise scientific principles of combustion, the chemical process where a substance reacts with oxygen to release energy. We interact with this process every single day. Whether it is the LPG stove in your kitchen, the diesel in a school bus, or the simple wax of a birthday candle, combustion is constantly at work around us. However, you will soon discover that not all burning is the same. We will explore the fascinating distinction between substances that burn with a vibrant, flickering flame, like magnesium or kerosene, and those that simply glow with intense heat, like charcoal. We will investigate the invisible rules that govern these reactions, specifically the concept of ignition temperature, the specific heat barrier that determines whether a matchstick stays dormant in your pocket or bursts into light when struck. But understanding combustion is not just about starting fires. It is equally about knowing how to stop them. We will learn the life-saving science behind fire control and the fire triangle, giving you the knowledge to understand how firefighters save lives. Finally, we will turn our eyes to the future by discussing fuel efficiency and the environment. As we analyze the structure of flames, from their dark inner zones to their invisible, hottest outer edges, we will also face the hard truths of pollution, acid rain, and global warming caused by burning fossil fuels. This chapter bridges the gap between basic chemistry and our real-world responsibilities as citizens of Earth. Let us ignite our curiosity and dive into the science of heat and light.
To begin our journey, we must first define the core concept of this chapter. In scientific terms, combustion is a chemical process in which a substance reacts with oxygen to give off heat. This is the textbook definition, but let's look closer. When we see a candle burning or a car engine running, we are witnessing combustion. The substance that undergoes this burning process is called a combustible substance, or more commonly, a fuel. Fuels are versatile. They can exist in three states: solid, liquid, and gas. During this process, energy is released. While heat is always produced, sometimes light is also given off, either as a flickering flame or as a glow, like a candle, or as a glow like burning charcoal. It is interesting to note that even our bodies perform a type of slow combustion. Food acts as a fuel for our body. It is broken down by reacting with oxygen, producing the heat essential for our survival. Is fuel alone enough to start a fire? No. We need to investigate the conditions required. The text describes a crucial experiment involving a candle and a glass chimney. Scenario A. When the chimney is open from the bottom, allowing air to flow, the candle burns freely. Scenario B. When the bottom supply of air is blocked, the flame flickers and produces smoke. Scenario C. When the top is also covered, cutting off air completely, the flame goes out. This proves a fundamental law. Air is necessary for combustion. However, air and fuel are still not enough. You have likely observed that a matchstick does not catch fire on its own while sitting in a box at room temperature. It needs a specific trigger. This brings us to the concept of ignition temperature. This is defined as the lowest temperature at which a substance catches fire. Different substances have different ignition temperatures. For example, kerosene oil and wood do not burn at room temperature. But if you heat kerosene just a little, it catches fire. Wood, however, requires much more heat to start burning. This tells us that the ignition temperature of kerosene is lower than that of wood. Substances that have very low ignition temperatures and catch fire easily with a flame are called inflammable substances. For example, petrol, alcohol, and LPG. To prove that a substance must reach its ignition temperature to burn, we look at activity 4.4. If you make a paper cup and heat it with a candle, it burns. However, if you fill that paper cup with water and heat it, the paper does not burn. Why? The heat supplied to the paper is transferred to the water by conduction. This transfer keeps the paper cooler than its ignition temperature, preventing combustion, while the water inside may even begin to boil. Understanding these fundamentals of combustion and ignition helps us grasp the science behind everyday phenomena and safety.
Now that we understand how to start a fire, we must understand how to stop it. This is crucial for safety. Firefighters operate on a simple scientific principle. To produce fire, 3 requirements must be met: fuel, air, and heat. Fuel is the substance burning, air supplies oxygen, and heat raises the temperature beyond the ignition point. This is often called the fire triangle. To extinguish a fire, we must remove one or more of these elements. We usually cannot remove the fuel. For instance, if a building is on fire, the whole building is the fuel. Therefore, fire extinguishers work by either cutting off the air supply, bringing down the temperature, or both. Water is the most common fire extinguisher. When firemen pour water on a fire, the water cools the combustible material. This brings its temperature below its ignition temperature, which stops the fire from spreading. Furthermore, the heat converts the water into water vapor, which surrounds the fuel, effectively cutting off the air supply. However, water has serious limitations: electrical fires. Water conducts electricity. If used on electrical equipment, it can harm the person fighting the fire. Another limitation is oil and petrol fires. Water is heavier than oil. If poured on an oil fire, the water sinks to the bottom, allowing the oil to continue burning on top. For electrical and oil fires, carbon dioxide, or CO2, is the best extinguisher. CO2 is heavier than oxygen, so it covers the fire like a blanket. By sitting between the fuel and the oxygen, it cuts off the contact and the fire dies. Additionally, when released from a cylinder, CO2 expands enormously and cools down, which helps lower the temperature of the fuel. Another benefit is that it usually does not damage electrical equipment. A fascinating side note on ignition control is the matchstick. Ancient Egyptians used pine wood dipped in sulfur. The modern safety match, developed 200 years ago, uses a safe chemical reaction. The head contains antimony trisulfide and potassium chlorate. The rubbing surface contains powdered glass and red phosphorus. When struck, friction turns red phosphorus into white phosphorus, which reacts with the potassium chlorate to ignite the antimony trisulfide. This controlled chemistry allows us to carry fires safely in our pockets.
Combustion is not always a slow burning process. We classify it into 3 distinct types based on speed and reaction. Rapid combustion occurs when a substance burns quickly, producing heat and light, like bringing a lighter near a gas stove. Spontaneous combustion is more dangerous, where a material suddenly bursts into flames without apparent cause, such as phosphorus burning in air at room temperature. This is also a risk in coal mines due to coal dust and in forests, leading to forest fires caused by heat or lightning. An explosion is a sudden reaction involving heat, light, sound, and the liberation of a large amount of gas, as seen when we ignite firecrackers. Pressure alone can also trigger an explosion in these materials. Not all burning substances produce a flame. A candle burns with a flame, but coal does not. Substances which vaporize during burning give flames. Kerosene oil and molten wax rise through the wick, turn into vapor, and burn as flames. Charcoal does not vaporize, so it only glows. If you look closely at a candle flame, it is not uniform. It has 3 distinct zones. We can analyze these zones through simple experiments involving glass slides and copper wires. The inner zone, or dark zone, is the area around the wick, containing unburnt wax vapors, and is the least hot part of the flame. The middle zone, or luminous zone, is the bright yellow part where partial combustion takes place. If you hold a glass plate here, a circular blackish ring forms, indicating the deposition of unburnt carbon particles. This zone is moderately hot. The outer zone, or non-luminous zone, is a faint blue zone at the edge, where complete combustion occurs due to plenty of air. If you hold a copper wire here, it turns red hot, proving that this is the hottest part of the flame. This temperature difference is why goldsmiths use the outermost zone of the flame with a metallic blowpipe to melt gold and silver. They need the maximum heat available to melt these metals. We rely on fuels for domestic and industrial energy. A fuel is any material that produces heat energy. However, not all fuels are equal. We strive to find an ideal fuel, though one likely doesn't exist perfectly. A good fuel should be readily available and cheap, burn easily in air at a moderate rate, produce a large amount of heat, leave behind no undesirable substances. To compare fuels, we look at their calorific value. This is the amount of heat energy produced on the complete combustion of 1 kilogram of a fuel. It is expressed in the unit kilojoules per kilogram. Looking at the data, we can see massive differences in efficiency. Cow dung cake, 6,000 to 8,000 kilojoules per kilogram. Wood, 17,000, 22,000 kilojoules per kilogram. Petrol, diesel, kerosene, 45,000 kilojoules per kilogram. LPG, 55,000 kilojoules per kilogram. Hydrogen, 150,000 kilojoules per kilogram. This explains why we prefer LPG over wood. It produces far more heat per kilogram and burns cleaner. While fuels are necessary, their consumption harms our environment. We must be aware of these 4 major impacts. Respiratory disease. Carbon fuels like wood, coal, and petroleum release unburnt carbon particles. These fine particles are dangerous pollutants that cause respiratory diseases like asthma. This is a major reason why rural use of wood is discouraged. Carbon monoxide poisoning. Incomplete combustion produces carbon monoxide, a tasteless, odorless, and poisonous gas. This is why it is dangerous to burn coal in a closed room. The CO gas produced can kill people sleeping inside. Global warming. Most fuels release carbon dioxide. Increased concentrations of CO2 in the air are believed to cause global warming, which is the rise in the Earth's atmospheric temperature. This leads to melting polar glaciers and rising sea levels, threatening coastal areas. Acid rain. Burning coal and diesel releases sulfur dioxide, a suffocating, corrosive gas. Petrol engines release oxides of nitrogen. When these oxides of sulfur and nitrogen dissolve in rainwater, they form acids. This is called acid rain. Acid rain is very harmful to crops, buildings, and soil. Because of these dangers, we are seeing a shift toward cleaner fuels. For example, CNG is replacing diesel and petrol in automobiles because it produces these harmful products in very small amounts, making it a cleaner fuel.